Okay, so the first question we're going to go over from the homework last night is number 27. From which section was that, Kevin?
2.4.
2.4, number 27. All right, so we're looking at number 27 from section 2.4 here. And so they're asking us to evaluate the function at different values of x based on the definition that they're giving us. So let's go ahead and do that. So f of 0, for instance, is going to be, well, we have to look at our domain to figure out where does 0 lie, between -1 and 2 or between 2 and 3? Between -1 and 2, right? So we're going to use that definition, this first definition right here, to go ahead and evaluate f of 0. So we're going to get 2 times 0 minus 4, which is just going to be -4. And f of 1 is going to be 1 cubed minus 2, which is going to be -1. And lastly, f of 2 is going to be, whoops, f of 1, I screwed that one up, didn't I? Looking at the wrong domain there. I should be between -1 and 2 there. So f of 1 is actually going to be 2 times 1 minus 4, because that's between -1 and 2, right? And so we'll get -2. And then for f of 2, we'll get 2 cubed, because now we're between 2 and 3. Ooh, but what did I screw up there? Why shouldn't it be that? Someone want to tell me?
X is just greater than 2.
Yeah, exactly. There we go. Yeah, if we look over here, it's, if x is equal to 2, that's on this domain right here, not this interval right here. And so it's still going to be defined by that one. So that might have been the issue there. 2, it's a little big, right? So it should be 2 times 2, which is 4, minus 4 is equal to 0. So those are our answers right there.
Okay, I like the graph if I was confused.
Yeah, this one, you don't necessarily need to graph it to be able to answer this question right here, because they're just asking you to evaluate it. So don't graph it if you don't have to. Just look at the value of x that you're evaluating it for and decide which definition you need to use based on the intervals that are designated there. Other questions from the homework? Is that the only one?
Pretty much overall.
Okay. Alrighty. Today we're going to talk about transformations of functions. And how that works, right? And so we have sort of a library of functions so far that we're familiar with, which I'm just going to go through and list the following off. So we have our current, all the types of functions we're familiar with, at least the basic versions of which we are familiar with. And we are going to use them as examples today when we're talking about transformations of functions. So for instance, we have the function y is equal to x, your basic linear function. We have y equals x squared, y equals x cubed, y equals the square root of x, y equals the cube root of x, y equals the absolute value of x, and y equals 1 over x. And so from the other day, we know what the graphs of all of these basic functions are called. And today, we're going to refer to these as our parent functions. Whoops. Because we are going to go ahead, let me just try and get that in there better, and we are going to do transformations of these parent functions to get new functions which are based off of them. So that's why they're called parent functions. Close enough. Okay. So we're going to be doing a lot of graphing today, so you're going to want to have your graphing calculators out. All right, today we're going to be doing a lot of graphing. And so I'm going to be using the Desmos graphing calculator here on the website. There were some issues with that yesterday, so I'm hoping it's just going to work. But bear with me if the graphs aren't showing up or so forth. But we're going to do our best here. All right, so today we're talking primarily or entirely about transformations. And so what we're going to do is we're just going to sort of start with a parent function. Let's start with a basic function like y equals x squared here. Right? Your basic parent function, y equals x squared. Right? And let's see what happens when we apply different types of operations to this particular expression right here, x squared. Now, the first most obvious thing we could do, sort of most basic thing we can do with this is just take the x squared. We can go ahead and add or subtract some value to it. And we see that if I go ahead and I add 2, it shifts it up by 2, right? It just pushed it up from its original location by 2. If I went ahead and I add 1, shifts it up by 1. If I add 3, shifts it up by 3. We can see right away that we're starting to see a pattern here, that the amount that I add to it is just going to do a vertical shift by that amount, right? Because we're just taking whatever that x squared was, which was the original y value, right? And we're adding 5 to it. So it makes sense that that's going to push it up by 5, right? Now, on the other hand, of course, if I subtract, we would expect it to do the opposite, right? Push it down. So if I go ahead and do that, I see I get -2, -3, -4, -5, and so forth, right? So adding or subtracting a value from the outside of the function is a vertical shift either up or down, right? So let me go ahead. Go away. So our conclusion from all this is that if we have some function y is equal to f of x, and we add some value to the outside, which we're going to call d, then this is a vertical, what we're going to call a translation. Anytime we just move something without changing the shape, that's a translation by d, either up or down, depending on whether d is positive or negative. Okay. So that's the first transformation that we're sort of observing here. And let's just go ahead and we're going to go ahead now, we're going to apply that to different types of functions to see that it has the same effect no matter what the parent function happens to be. So now let's go and just check to make sure that this whole idea actually applies to other types of functions. So we'll start off here with the function y is equal to the square root of x, right? And then if we go ahead here and apply that same type of transformation, whoops, got to make sure it's not on the inside though, like +2, look at that, it shifts it up by 2. If I do -2, it shifts it down by 2, right? If I do +6, it shifts it up by 6. We can see that same effect is being had on that particular function. Let's try another one. Let's try the function 1 over x, the reciprocal function. There's that function right there. It's a nice little hyperbola. And if we go ahead and start adding and subtracting stuff to that function, look at that. It moves it up by 3. I can move it down by 2. So we're seeing this is sort of a universal rule no matter what parent function we're talking about. Let's just do one more. Right? And if we go ahead here and let's say add 3, goes up by 3. Maybe we want to subtract 2, goes down by 2. So no matter what family of function we're talking about, if I add something to the outside of the function or subtract something from the outside of the function, that will always result in a vertical translation. All right, so let's go ahead and try a different type of transformation now. So in all these cases that we've seen so far, we've added or subtracted something from the outside of the function. What happens if we instead do that in a different order? So for instance, if I have the function y equals, let's start off with just our basic quadratic, x squared. Now instead of going ahead and adding some number to the outside of y is equal to x squared, what I'm going to do here is I'm going to put a set of parentheses around here. Not like that. That's more what I was going for. And I'm going to add or subtract to the input, the argument, instead of adding or subtracting from the result, the y value x squared. I'm going to add or subtract to whatever x happens to be. So if I go ahead and do that, what if I go ahead and do -2? Look at that, it shifted it to the right by 2. Right? On the other hand, what if I do +2? Whoops, shifts it to the left by 2. What if I do -5? to the right by 5, and so forth. You sort of you're seeing what I'm getting at, I'm sure. That if we add or subtract a value from the inside of the function, and by inside I mean inside those parentheses right there, we add or subtract from the value of x before we do the operation. In this case, the operation I'm talking about is the x plus 4 squared operation. Then in that instance, we actually do a horizontal shift. And what's the reason for that? The best way to describe it is, what you're doing is you're taking whatever x value that you were originally going to put in, let's say x was 1, and you're finding f of 1, you plug it in, you're going to add 4 to that x value. So it's going to actually give you the x value at 5 for the normal function, the parent function. And so what that means is, if I'm getting the x value, so right here, if I plug in 1 for x, I'm actually going to be evaluating 5 squared, right? So that's what x squared looks like when x equals 5. And so it's essentially at 1, what's happening at 5 is already occurring. And so it's taking the whole function and pushing it backwards, right? It's already to that point as a result. And that's also why it's sort of an inverse of what you would expect. If you add, you actually shift it to the left. And if you subtract, you shift it to the right. So let's go ahead and summarize that. So with horizontal translations, if I have the function y, if I have the function y is equal to f of, and instead of adding to the outside, if I add to the actual argument or subtract from the argument, the independent variable x, by whatever c is, we'll call that c, then this is a horizontal translation. Right, and it is a horizontal translation to the left if c is positive, and it's a horizontal translation to the right if c is negative. So unlike vertical translations where things behave exactly as we would expect them, we add or subtract, it goes up or down, up if it's positive, down if it's negative. With horizontal translations, it's the opposite of what we expect essentially. We go to the left if c is positive. We go to the right if c is negative. Okay, so that's probably the hardest thing to keep straight as far as these transformations are concerned, is that horizontal shifts act in that sort of strange way. Let's go ahead and go on to talking about vertical and horizontal expansions and contractions. All right, now let's go ahead and investigate some expansions and contractions here. Now, in the previous examples with horizontal shifts and horizontal translations and vertical translations, we were adding and subtracting. What happens if we start multiplying and dividing the original function? Let's go ahead and we'll start off with our original function, y is equal to x squared here. Right? And let's try to go ahead and multiply this by something. So we have a regular old y is equal to x squared. What happens if I multiply it by 2? What happened there? It got sort of skinnier, but why is that? Why is it getting skinnier as a result? Can someone describe that to me? Or answer that question? Why would it get skinnier if I multiplied it? I think if I sort of thought about it on a superficial level, I would think, well, multiplying it makes bigger, that means wider, right? But why does it mean it's actually skinnier? What is it doing to every single one of those y values? What? It's making it bigger, so it's stretching it vertically, right? It's taking every single y value and pushing it up. So by pushing this graph right here up, you're actually making it look skinnier because everything's getting stretched. Imagine if you go ahead and you take like a rubber band and you stretch it out. What happens to it? It gets skinnier, right? Because you're stretching everything. It's the same general idea. And so if I multiply by a bigger number, it gets even skinnier. Skinnier yet if I make it 6. How could I make it, and of course I make it 1, that doesn't change anything, right? How could I make this narrower, do you think? Or sorry, wider instead of skinnier? What if I try a number less than 1? Ooh, that's sort of a little bit skinnier, or a little bit wider, right? Yet wider, and yet wider still, right? So we're seeing the same thing happening there. Let's try the same idea on a different type of function. Let's go with the square root function. So let's say square root of x, right? And we go ahead and we take and multiply the outside. Once again, what we're doing is we're multiplying the outside right now. Might be a different situation if we multiply the inside. multiply it by 3. Oh, look at that. Stretch it, and that's pretty obvious. It just pulled everything up, right? A little bit less, so it's a little bit not quite as pulled up. 4, 5, 6, 7, keeps getting pulled up farther and farther. And then, of course, once again, if I make this a number less than 1, whoops, it's going to make it, it's going to push it down, which in the case of a square root function doesn't necessarily make it look skinnier. It makes it look sort of lower. It's just with the quadratics, it sort of makes it skinnier. But it's really, it's a horizontal compression if it's less than 1 and more than 0. And if it's a horizontal expansion if it's a value greater than 1. Let's just confirm that by trying one more type of function, maybe the absolute value function. No, how about the x cubed function? Why not that instead? So here's x cubed. Just to confirm that. This one probably is going to look skinnier just because of the way it looks, right? Yep, a little skinnier, even skinnier, even skinnier yet. So yes, that's sort of confirmed. And then if we go and put a smaller number than 1, makes it wider, 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 whoops, even wider, right? And so if I multiply the outside of a function by a number, it's going to either be a vertical contraction or a vertical expansion. Let's go ahead and summarize that. All right, so if I have y is equal to a times my original function f of x, right, no matter what f of x is, no matter what family that happens to be, right, this is going to give me a vertical either expansion or the opposite of that, a contraction. Right? Now, if a is greater than 1, it gives me an expansion, right? Vertical expansion. And if a is less than 1 and greater than 0, it's going to be a compression. Notice I'm restricting a from being negative for the time being. We'll talk about what happens when that value becomes negative later. But for now, we're just going to keep a between either 0 and 1 or greater than 1. So that's how we have vertical expansions and contractions. All right, whoops. We're going to go ahead now and talk about, we just talked about vertical expansions and compressions, so you can probably imagine we'll probably talk about horizontal expansions and compressions now. And so just like we did with vertical and horizontal translations, in the last example with vertical and horizontal compressions and expansions, we multiply the outside of a number by something, the outside of a function by some number. We're going to go ahead now and multiply the inside of a function by that, or by a number of some sort. Let's go ahead first and look at the function y is equal to x cubed. We'll use that as an example. All right, so if we go ahead here, see if I can do this here, and instead of multiplying the outside, whatever the resultant y value was, by some number, we're going to go ahead and we're going to take and multiply the argument x by a number instead. So for instance, let's say 3x. If we go ahead and do that, we're going to see that if we multiply the inside, what's actually happening, right, is that we are making it get to those x values faster than they normally would. So if I plug in x equals 1, I'm actually getting x equals 3, right? So what it's doing is it's taking that x value from the right and it's pulling it in and taking whatever y value occurred at 3, and it's actually occurring at x equals 1 now. So if you can imagine, it's just like sort of reaching over, grabbing whatever the y value was at x equals 3 and pulling it over to x equals 1. And if I were to plug in 2, it's going to do 2 times 3, which is going to be 6. And it's going to grab the x value, the y value that would normally occur at 6, and pull it over to where 2 is. All right, so it's pulling everything in horizontally, right? So this is what's going to be called a horizontal contraction. And it makes sense because it looks skinnier, right? And if I go ahead and make it bigger, it gets even skinnier. And what do you think is going to happen if I make it between 0 and 1? It's going to get what? Wider, much wider. 0.2, a little bit less wide. 0.1, even wider. 0.9, about the same, but a little bit wider, right? So if we multiply the inside of a function by that, we get a horizontal contraction or expansion. Let's look at another example. Let's try the function 1 over x, our good old reciprocal function there. And in the bottom here, we'll go ahead and multiply this guy by 2. And a little bit of a contraction horizontally there. It pulled it in a little bit. Let's make it like 7. Pulls it in a lot, right? What if I make it 11? Even more. What if I make it 100? Really pulls it in there, right? So I'm really doing a big horizontal contraction there. And if, of course, I make it like 0.5, sort of pushes it out to the right and to the left. 0.6 pushes it out more, or sorry, a little less. 0.2 pushes it out more. 0.1. 0.01. Graph. Go ahead and graph that. Oh, it's just so big you can't even see it. Yeah, that's what happened there. All right, so we can see that by multiplying the inside of a function, we get a horizontal horizontal contraction or expansion, right? So let's go ahead and summarize that. So if we have the function y is equal to f of, we're going to have this be b, bx. B is a horizontal is a horizontal expansion or compression. Right, and once again, if b is greater than 1, then it is a compression. So it's just like, so we see that just like with horizontal translations, right? If we're doing something to the inside, to the argument of the function, it has the inverse effect that we would think it would have. So if b is greater than 1, we get a compression horizontally. And if b is less than 1 and greater than 0, we get an expansion. So this is sort of the opposite of the effect that we would have with vertical compressions and expansions, where if we multiply the outside of the function by a, right, and that's larger than 1, it's an expansion. The opposite of what we get if we multiply the inside of the function, we get a compression, right? So in general, just remember that anything done to the inside of the function, or to the argument, the x value, results in a translation opposite of what you would expect. Opposite of expectation, let's say. Okay? So, horizontal expansions, contractions, vertical expansions, contractions, vertical translations, horizontal translations. Those are the 4 types of transformations we've seen so far. Let's go ahead and summarize that really quickly. Y is equal to A times F of, and so what I'm going to do here is do B times, why would I want to do that? Times X plus C plus D, right? So this sort of just summarizes all the different possible transformations I could do to any given function, right? And notice it's really important that inside here, because of the order of operations, the shift, the horizontal shift here, has to be done before the vertical compression or expansion. So we're gonna go ahead here and summarize all these different things. C gives me a horizontal translation. D is a vertical translation. A is a vertical stretch or shrink. And B is a horizontal stretch or shrink. Another theme you're probably starting to see here is that anything done to the inside, done to the argument of the function, the x value, b and c, affects the horizontal behavior of the function, whether it's a translation or expansion or compression. And anything done to the outside, a and d here, right, done to the outside affects the vertical sort of behavior of the function. Okay. So these are all different types of translations. As soon as we get done with our break, we'll sort of put those all together and see how we can use those to graph a function. So why don't you take a quick 5-minute break? Okay, one last type of transformation we want to take a look at is the possibility of reflections. All right, so let's go ahead and do that. All right, so the other type of transformation we want to talk about are reflections. And reflections occur, it turns out, when, so let's start off with x squared, when we throw a negative either on the inside or on the outside of the function. So if we start off with our parent function, basic quadratic x squared, what happens if we throw a negative out front of it? Looks like we have a translation where it just flips it over the x-axis right there. Interesting. Let's see what happens when I do that with another type of function. Let's take the square root of x function. So there's the square root of x function. What if we go ahead and throw a negative on the outside? Same deal, flips it over the x-axis, right? Let's go ahead and do the x cubed function. Throw a negative up front of that one. Bam, also flips it over the x-axis, right? I think we're starting to get the trick here. Let's look at one last one. Let's take the function 1 over x and make it the function negative 1 over x. Also flips it, rotates it, reflects it, however you want to say that, over the x-axis. On the other hand, what happens if we do this same operation, we take the opposite of the value, but on the inside, if we take the opposite of the argument. So let's go back to our x squared here, and let's go ahead and apply this same type of idea here. Whoops. On the inside. All right, so what if we go ahead and make the inside of the function negative? Nothing happened to the quadratic function, interestingly. Why is that from an algebraic perspective? Why did that not change anything?
Because a negative number squared is possible.
Yeah, negative x squared is still x squared. It turns out this has to do with the fact that it's symmetrical about the y-axis. Because what if we go ahead and do this to the function x cubed? So we start off with x cubed here. Right? And what if we make the inside of that negative? So I got to go ahead and do this. Nope, that's not what I wanted. So now it's just, let's make this x cubed. And we see that it actually rotates it or flips it over the y-axis. And because x cubed is not symmetrical, let's graph these side by side just so we can see this better. Right, we can see that it rotated or flipped it over the y-axis compared to the original function, right? And that's because x cubed is not symmetric around the y-axis. We can actually see it. Whereas x squared is symmetric, so even if you flip it over the y-axis, you still have the same function. Algebraically, it's because squaring it makes something positive. Let's look at another example. Let's go to the square root function. And we will go ahead. I'll graph these two side by side. And let's go ahead if we do square root of negative x here. Flip it over the y-axis, right? Let's do, instead of the square root function, we'll do the reciprocal function. And if we go ahead and make it negative x, whoops, I did the same exact thing as flipping it over the x-axis, right? We're going to see that these, so in some cases, it's going to have the same effect, right? They're the same function. 1 over negative x is the same as negative 1 over x. Well, that's just because algebraically that's the same exact expression. So sometimes there's no difference depending on the algebraic sort of construction of the function. In this case, for the function 1 over x, flipping it over the x-axis accomplishes the same exact thing as rotating it over the y-axis. Doesn't make a difference one way or the other. Whereas in other functions, like the x cubed function, we see that it does make a pretty big difference. So the function x cubed, let's go back to that one for a second, versus negative x cubed versus, well, in fact, is this going to be the same too? It is, isn't it? Because negative x cubed algebraically is the same as negative x cubed. So you're looking at this going, well, does it ever make a difference? Well, in the case of the square root function, it did, right? So in the case of a lot of functions, flipping over the x-axis accomplishes the same thing as flipping it over the y-axis, except for the square root of x function, just because it is very non-symmetric, right? So we do see a distinct difference in a rotation over the y-axis versus a rotation over the x-axis with the function square root of x. But in the case of a lot of functions, as a result of their shape and their symmetry, reflecting over the y-axis in some cases is the same as reflecting over the x-axis as far as the result is concerned. So you got to look at the algebraic construction to sort of get a hint as to what that's going to be. But in any case, taking a negative on the inside is a rotation around the x-axis. Which is sort of, we're affecting the horizontal. Once again, if we're doing an operation to the inside of the function, right, and we're having an effect on the horizontal sort of properties of the function, and if we do when we do that negative on the outside, we do an operation to the outside of the function, we're having an effect on the vertical properties of the function. So that's a common theme here with transformations. So let's go ahead on the next page and summarize this, or on the same page. So, if I have y is equal to negative f of x, this is a reflection over the x-axis, right? On the other hand, if I have y is equal to f of negative x, this is going to be a reflection over the y-axis. Okay. So that pretty much covers all the different type of possible transformations we might have to do. But the question becomes, what if we start combining these? If we apply a single transformation, it's pretty obvious how we're going to do that and how that's going to look on the graph. But if we start applying multiple transformations at once, that's when it gets a little bit trickier. So for instance, let's look at a function like the following. All right. So first of all, for this function, square root of 2 minus x plus 3, what would the parent function be? What's my parent function that this is based off of? Yep. And so if we know what the square root of x looks like, so we're going to do this by hand for this one right here, then maybe we can go ahead and graph our new function here. So I'm going to start off just by graphing square root of x, just so we know what that looks like, right? There's my parent function. Now, let's try and identify what transformations are being done here. Now, what transformations are being done? Well, what's the 3 on the outside here doing? What's this? What's that 3 doing? Vertical translation. Up, right? By 3. So we're going to push it up by 3. Now, the tricky part is on the inside here. We have the 2 minus x. So what do we think is going on here? There's definitely some sort of a horizontal translation, but it's 2 minus x instead of x minus 2. What does that mean? That's the opposite of something, isn't it? How could we rewrite this so that it's more obvious what type of transformation is being done there? What's the opposite of 2 minus x? The opposite of 2 minus x is x minus 2. So would this be true? Whoops. God, sometimes this thing. Let's try that again. So would this be true? Would you agree? So, let me also rewrite that. Sorry, I'm being a perfectionist here. All right, good enough. So, what do we think are the transformations that are occurring in here? What are the two distinct transformations that we have? What's the negative on the outside they're doing? Reflection over y or x. It's on the inside of the square root. Yes, reflection over y. Over y-axis. And what else? To the right by 2. And horizontal translation. Right by 2. So we have a vertical translation up by 3. We have a reflection over the y-axis, and we have a horizontal translation to the right by 2. Let's go ahead and use those and we'll use the parent function to help us figure out what this is going to look like. So the first thing we should do always is the stuff that's happening on the inside, and we're going to work our way out. So it's a reflection over the y-axis, first of all, right? Or actually, sorry, let's work our way from the inside out. The first thing we should do is push it to the right by 2, right? So I'm going to just draw successive transformations here. So I'm going to push it to the right by 2. Let's say this is... Let's say this is 2 right here. And then let's go ahead and flip it over the x-axis. Right? Oh, sorry, I'm flipping over the y-axis. Thank you. I'm just going to go ahead and erase all of this because this is... Now I'll just do this instead. Yes. Okay, let's try that again. So then we're flipping it over the y-axis, so that's going to be a rotation that's going to look like this, right? And then what's the last thing we're going to do on the outside there? Shift it up by 3, right? So let's say here's 3, so now it's going to look like this, right? So my final result would be this guy right here, right? So we push it to the right by 2. We rotate it around the y-axis, which is essentially just to rotate it horizontally 90 degrees, or sort of rotate it to the left 90 degrees, and then push it up by 3. Let's go ahead and confirm that by plugging it into the graphing calculator to see if that actually does look like what we think it looks like. Right, so let's go ahead and graph that. So if we plug this into the graphing calculator, y is equal to square root of 2 minus x, and then on the outside we do plus 3. We get what we expected, right? So we shift it right by 2, we flip it over the y-axis, or just, we can think of it as just flipping it over the vertical axis, right? Whatever that, because the y-axis essentially, once we've shifted it over by 2, what it thinks is the y-axis is the line y is equal to, or x is equal to 2, right? So essentially, we just think of that as a rotation over the vertical axis, that the negative x minus 2 part, and then the plus 3. The last thing we do is shift it up by 3. Okay. I'm going to give you one that I'm going to have you graph on your own. Go ahead and graph me the function y is equal to 2 over x plus 1 minus 2. Okay, go ahead and give that a shot. So the first thing we want to do is identify the parent function's graph, which is the graph of y of 1 over x, and we'll go ahead and graph that. The second thing we should do is identify the type of transformations that have occurred. So it looks like there's 3 distinct transformations here, 3 distinct operations being done. So what are those? What's the first one? Doesn't matter what order, just tell me one of them.
The vertical shift downwards.
Vertical shift down 2. What's the next one? Any of the other 2 is fine.
To the left one.
To the left by 1, yeah. And that's a translation. And lastly, what's the 2 on top doing?
Pull it in more or push it?
Is it a vertical or horizontal expansion or contraction? Is it happening is it being done to the outside of the function? Could I rewrite this as y is equal to 2 times 1 over x plus 1? Would that be the same thing algebraically? So if it's done to the outside, is it horizontal or vertical? If we do anything to the outside, it affects the horizontal or vertical nature of the function. Vertical, yeah. So it's going to be a vertical expansion or contraction? Expansion, yes. So it's vertical stretch by a factor of 2. So let's go ahead and apply these. So vertical shift down. Let's do the stuff from the inside first, like I said. So left by 1. And I'm going to draw all of these out, and then we'll go ahead and might be a little bit confusing. So left by 1. So it's going to get shifted to the left by 1. Right? And then it's going to be a vertical stretch by 2, which just means it's going to get steeper. Right? Everything's going to get pushed up by a little bit. Whoops. So it's going to be steeper, everything's getting pushed up, right? Steeper. And then lastly, it's going to be a vertical shift down by 2. So take that and push it down by 2. So, so it's going to look like this. Right? And so that's sort of our final. That is really, I should have done that last part. Whatever. I'm going to have a really hard time erasing that. But that is what the function should look like, right? Let's go ahead and confirm that in the graphing calculator. All right, so we go and graph this. We get y is equal to 2 over x plus 1. And then was it minus 3 or minus 2? And so much as we expected, that's what it ends up looking like, right? Any questions about that? All right, now let's work it the other way around. I'm going to give you the parent function on this next example to do, and I want you to write the function that has those properties. So if I give you the function y is equal to square root of x, that's the parent function. I want you to do 3 translations to it. Do a horizontal. Whoops. Horizontal shift right 2. I want you to do a horizontal expansion by 3. I want you to do a reflection over the y-axis and vertical translation down or up by 4. So horizontal shift to the right by 2, a horizontal expansion by 3, a reflection over the y-axis, and a vertical translation up by 4. All right, so I should work my way from the inside out here. I already sort of started working on it here. So start off by subtracting 2 for your horizontal shift right 2. Horizontal expansion by 3. For a horizontal expansion, right, the number has to be smaller than 1 and greater than 0, right? For it to be an expansion horizontally that we're multiplying the inside by. And so if it's a horizontal expansion by 3, what I have to do is multiply the inside by 1/3, right? And then it's a reflection over the y-axis, which is also on the inside, so the whole thing on the inside has to be negative. And then lastly, it's a vertical translation up by 4, right? So that will accomplish what we want to accomplish right there. All right. Let's look at one really quick example. We're almost out of time, but I want to fit this in here. Imagine in this last example that we have a function f of x that has x-intercepts of -2 and 7. Right? What would be the x-intercepts of the function f of x minus 2? What would be the x-intercepts of the function f of -x? And what would be the x-intercepts of the function 2 times f of x? Now for the first one, what if we shift, doing f of x minus 2 shifts everything in the function to the left or right by 2? To the right by 2. So if the original intercepts were -2 and 7 and everything's getting shifted to the right by 2, what should the new intercepts be? Yeah, 0 and 9. Now if I take, and what type of translation is this? Reflection over what? Over the y-axis, yeah. So what's going to happen if I flip everything over the y-axis? What are my x-intercepts going to be?
-7 and 2.
Yep. Right, because 7 gets flipped over to -7, and -2 gets flipped over to +2. So the intercepts will be -7 and 2. And what happens if I multiply the entire thing by 2? That's a vertical expansion by 2, right? What would we expect if we just sort of shift everything up? Sorry. What values of x are going to make the function 0, the y value 0? So we have the function y is equal to 2f of x. Does it matter? Are the same values going to make... So if I take 2 and multiply it by 0, is that any different than just having 0? So f of x is going to be... Because f of x itself, before we multiply by 2, is still going to be 0 at -2 and 7. If I multiply 0 by 2, it's still going to be 0. So it's still going to be 0 at -2 and 7, algebraically, right? And so it's actually not going to affect the x-intercepts. They're still going to be -2 and 7. Right? I'll ask you, there's a couple of questions like that in the homework tonight. All right, that's it for today. So let me put the homework up on the board here. And so that will be your homework assignment for tonight. There was a new handout, 2.5, that I emailed out to everyone. These last two right here, these are from the old handout that you should already have from sections 2.3 and 2.4 on pages 88 and 98 of your handouts, right? But this part here is all from the new handout, which I gave in class today and which I will email out tonight as PDF. All right, guys, have a great weekend. See everyone on Monday.